It's a pleasure to be here, and today I'm going to be talking about safe coding with LLMs and whether Scala could potentially be the silver bullet to make the code generate safe. But first, who we are. This is a project that was mostly done by Alexander Sternfeld, a research engineer in our lab that unfortunately couldn't come. So I'll try to present to the best of my ability, having supervised the project. I am assistant professor at Informatics Institute of Ashu SSO, co-founder of Gen Learning Center. I contributed to books on the topic. I'm assembly PI at Swiss AI Initiative. I'm an organizer of several workshops on LLMs and security and scientific editor of LLMs in cybersecurity book. However, I'm a machine learning expert first and foremost, not really a Scala expert. Alexander on his side is a research engineer. He's also contributing to serving stack and security at Swiss AI Initiative. He's a world-class mountaineer, which is the reason he's not entirely here. And he's as well a machine learning, not a Scala expert either. So the question is, what are we doing at Scala Days? Well, we have a hypothesis test. For some of you that might remember my face, in 2023 in Madrid, I gave a keynote at Scala Days where I made a hypothesis that Scala plus coding LLMs is awesomeness. So, why and how? First of all, machine learning and Scala share a core concept that you might guess. This is a function. This is a function as well. This function is handcrafted to be safe and secure and do what you're expecting to do it. This function is learned, and in a lot of cases, we don't really know what it's going to be doing. And it's definitely most of the time not secure. Most notably, when we train a machine learning function to do something, it's only going to do good this thing. So for instance, we have now models that are pretty good at recognize handwriting and transform it into digits, and we had them for now close to 35 years. We still don't have models that are able to figure out which of those images are chihuahuas and which are muffins. So the question with machine learning function is not as much how they learn, but more what they learn these days. And I'm not going to do an entire course of introduction to machine learning. That would be much longer talk and probably not really interesting to you. But the TLDR of today's machine learning is that you train neural networks that on each layer learn more and more general features. So you start with things that basically learn most basic elements and combine them to learn slightly more complicated elements, then more and more elements. A very good illustration to it is from talk by Yann Lequin from around 2015, where he shows this picture of a neural network recognizing that the car in the car, and you can see that low-level features, not really informative, mid-level features, you barely start understanding. However, in high-level features, you recognize the wheel, you kind of recognize the signs, handles, etc. So the idea is to have models that do everything pretty well, is to do an everything bagel. So we take models and we train it on everything that we can find so that they have features that they can later use to do other things. What does it mean for training LLMs, text LLMs? Well, here the everything bagel is the World Wide Web. You take the entirety of the World Wide Web and you pre-train a model on it for the next word prediction. And that gives you low-level features, relationship between words, mid-level features, relationship between sentences. Then you get a model that's able to output something that looks like text, but that doesn't make much sense. Definitely wouldn't confuse anybody in believing that it knows what it's saying. So the next thing, and kind of the revolution that took place around 2022, is to instruction tune them. Basically, you take a pre-trained model language and you give it examples of answering questions, and you create those high-level features, and you also increase the amount of data you're putting in, and you end up with what are LLMs. So InstructGPT, ChatGPT, Llama, QN, etc., that are able to have a conversation with you as if they were a helpful assistant, but underneath is still an LLM that has ingested the entire World Web and is using high-level features to predict the next token. Good. What does it mean for coding LLMs? Basically, coding LLMs work in the same way, except they're pre-trained on lots and lots and lots of code, usually scrapped from GitHub. And what you do, you took sometimes pre-trained, sometimes non-pre-trained model, and you feed it. You provide context, which is usually the name of the function, comments about what it wants to do, and you make it generate code. And then you go in the other sense, you give it code, and you make it generate the annotation, informative names of variables, informative name of function, etc., etc., etc. This has several implications. The problem number one is LLMs are mainstream. They need a lot of code, and they need a lot of annotation. Which means that if you take this RedMonk index of programming languages popularity, you need things that have a lot of repositories on GitHub, so a lot of code, and a lot of answers on Stack Overflow to understand what this code is actually doing. That's why the vast majority of LLMs will illustrate how well they're coding with extremely popular languages such as Python, Java, C++, sometimes CSS, sometimes HTML. More advanced LLMs these days will try to venture in the territory of slightly less mainstream language, but still very mainstream. So R, Swift, Scala, Kotlin, Rust, PowerShell. And finally, if you're really experimental, you can try to push them into the territory of Fortran, Erlang, Julia, Elixir, and sometimes get something that works, but mostly you're expecting it to remain experimental. And if you're going to go anywhere else, good luck. There's very good chances that you're not getting much out. Here be dragons. The second problem is that LLMs are currently destroying their training data. I mentioned that Stack Overflow is critical for LLMs to understand what snippets of code are doing, thanks to a lot of textual explanation of snippets of code based on human exchanges. Since the release of Copilot and more recently ChatGPT, the usage of Stack Overflow is dropping. So every single feature that gets introduced into the languages starting from 2022 is unlikely to be reflected on the data sources that LLMs are going to be training on. Hence, they're unlikely to reuse them down the line. The second problem is that LLMs generate a lot of snippets of code that people will then try to insert as authentic code or authentic responses on Stack Overflow. This is a problem that's much more visual in the image generation, but is exactly the same in code generation and text generation. For instance, if today you look at the baby peacock, the vast majority of the results are AI-generated images of what people would think baby peacock would look like, and not this kind of chicken, small chick, that doesn't look like much. And the third problem is coding LLMs code is insecure and there's no improvement in sight. I'm going to go with something that we have done in our lab to show it back in 2023, but it didn't change, don't worry. So there's this amazing paper, Asleep at the Keyboard, that gives a set of vulnerabilities for GitHub Copilot code contribution from 2021. It's a basic one. They found a couple of prompts for which GitHub was generating insecure code, trivially insecure, called them vulnerability. OK, let's check more recent models. CodeLlama 34B, CodeLlama 70B Instruct that has been pre-trained with Purple Llama. That's supposed to be pretty secure. Gamma 7B, Quen3 Coder 30B that was released only a couple of weeks ago. And basically what you can see is that here at the bottom is the prevalence of the vulnerability in generated code. And you can see that all of them generate code that in some cases is vulnerable in 100% of the cases. And that's even for models released today, 4 years later. If you go to software engineering people and you say, we have critical vulnerabilities reported for 4 years that haven't been patched in the most mainstream products, they're visibly going to be very upset and probably patch them pretty fast. In LLM land, it doesn't get patched. And there's actually reasons why it doesn't get patched that I'll happily extend at some other time, but not the focus of the talk today. And finally, the problem 4 is that we're all becoming children of the magenta line. Who understands this expression, children of the magenta line? Oh, awesome. You're in for a treat. Basically, imperfect machine can make imperfect decisions. So far, everybody agrees, right? You can add human into the loop, and that's what a lot of people say that we need to do for imperfect machines. However, if the machine is correct often enough, the human will always defer to it and will fail to detect and respond to the machine failing. This is an observation from the pilot training and aeronautics industry from the late 90s, where in the 50s, 60s, 70s, the entire discourse about why planes crash was human error, human error, human error, so let's build autopilots to remove human error. Pilots works great, vast majority of the time, but when you find yourself in corner cases, they stop, hand the control to the pilots, and the most frequent conversation you could hear in the black box recordings back at the time in the cockpits, oh, what the heck is the autopilot doing? I have no idea. Should we do something about it? Ah, no, it's figure it out. And there's this amazing talk by Captain Warren Vanderberg from 1997 that I highly recommend you watch on YouTube. It's probably 15 minutes of your time that would be really well invested. That called this effect and those pilots children of the magenta line because they would also always follow the magenta line of autopilot and never deviate this. And this unfortunately has led to a lot of crashes that already by the time he was making the talk have killed over 1,000 of people, and then in subsequent years before the pilot training was adjusted have killed even more people. The thing is that pilot crash planes. Software has eaten the world, so crashing software will crash the world. Now, that's kind of things that keep me up at night. So to be able to sleep better, I really want to find an answer to the question, how do we still write the safe mission-critical code? And if you ask this question to people in cybersecurity, they will pretty frequently answer to you, yes, formal verification is the answer, that's what we should be doing, because we've been trying to do it for a very long time, it's bulletproof correctness, bulletproof safety. However, when you try to press a little bit people in formal verification, they will say that actually it's not that easy. You need to know what you're trying to prove. You need to provide proof scaffolds for formal provers. You need to use formal verification-friendly language, and you need to write verifiable code. And if you look at the formal verification-friendly language, and you go back to what LLMs can generate, there's really not that much. There's obviously Scala. There's Swift. And there's Rust. And that's about what you'll be able to get out of people if you ask them, okay, what we can even try to verify, what have sufficient annotation and sufficient instruments in the language to do it. The problem with Swift is it's mostly used for user interface in public repositories. The vast majority of the code is interaction with user interface, which is great, but it's not really relevant to writing mission-critical code. Rust, once again, based on the conversation with experts, formal proving is just starting, which is a great thing. There's already existing tools. However, LLMs are pre-trained in the code that has existed for a while, so they need a long history. And Rust is still a fairly young language, at least widely used. Finally, Scala. Scala is interesting. It has long-standing interest in verification, so there's definitely scaffolding for it in the existing repositories. Language and verifiers are taught academically, which is great for LLMs because they have a lot of annotation to understand what they're trying to do. And finally, which is very relevant to us, is that we can come and annoy LAMP people when we have questions. So Scala was obviously our choice. Now, we focused on stainless. What is stainless verifier? It's developed by Lara Lab at the PFL, Victor Koncha Group. You should go see posters. It's a really nifty tool. It's been developed since 2013. It's stored as part of EPFL courses. So we have lots of open training data from students that have gone through this course and contributing their exercises. So we're really expecting that if LLMs can do formal verification, using something from the class and asking them to generate both the code and verification should work well. So the approach, take a course task, prompt LLMs with this task, generate Scala code, and generate stainless contracts. And if this seems as a great idea, it is, and it has been suggested by Hamza, who has taken the course and who has provided us with more details about how it works. So basically what we did, the code an LLM, coding Llama 70B works pretty good. We told it to implement a factorial in Scala and write stainless formal verification contract, and we provided a few short examples from the correct Scala and correct stainless contracts. And it basically generated us Scala code and stainless contracts. Scala code is not really interesting. And at first sight, it was actually working. It seems to be very fine. However, and if you're familiar with stainless, you're already seeing the problem. When it's writing the contracts, it's using the @library. @library means that please trust this is true. We're importing it from library. Somebody else proved it. Nobody proved it. So LLMs gaslight you into saying that, hey, We formally verified it. It's great. It's passing. Please accept it. And this is a toy example of a factorial. Imagine a bug like this in a mission-critical code in a code base that's several tens of thousands of lines long. Start seeing the problem. And the thing is that it's not just because we used the wrong model or because stainless is not sufficiently popular. This is consistent with other reports. For instance, there's a team at Forge 25 that tried to do the same thing in C. It was very fast using GPT-4o, so much better model, more widespread language. Very fast is about as popular as stainless from what we saw. But they got the same result. They had to manually repair both the proofs, and even in this case, the best they were getting was approximately 7% of proofs in principle. OK, formal verification failed. So basically, at this point, what we did, we went to annoy LLM people, and we asked them, OK, how do people write safe Scala in real world? What do they do? Unfortunately, at this time, Hamza was joined by Oliver, probably to be able to sustain a little bit better all the pressure we were putting on them with the questions. And basically, they explained to us that the vast majority of people use Scala types. Pros, the correctness is ensured by compile. If it compiles and you used things correctly, it should be working, and it's widely used in the wild, which is amazing. There's a lot of training code as well. However, you need to define informative types, you need to correctly constrain types, and to use the relevant type operation and logic from Scala to even get anything close. So we tried, hell, why not? Let's try it. Baseline, implement risky tasks in Scala. Baseline Scala code. Robust, implement risky tasks in Scala. Mind safety and use Scala types. Robust Scala code. Not the best. Should at least show if it works. And it does. Basically, this is correctness for a couple of toy examples. Average age, Fibonacci number, which is something that's currently used in the classes for the proofs. Matrix multiplication, matrix convolution, that as we as Python programmers have eaten a lot of runtime exceptions over the years. It helps. Not always. Sometimes it makes things worse, but it helps. And if we look at the safety, it also helps, and actually much more frequently. So what we did, we decided to figure out why it helped, and we focused on the robust to injection and looked at several coding LLMs. Robustness to injection is basically something that's generally referred to CVE 79. Cross-site scripting is one of the biggest examples. Basically, cross-site scripting, fairly common error. A lot of people writing code will mitigate it. A lot of languages have built-in safety against it. However, when LLMs are generating, they tend to generate code that's not that secure. And you cannot really say in advance which one will be and which will be not. Once again, apologize for Python. This is 2 prompts to do exactly the same thing. We're asking a Flask application using Python, Jinja, that will generate an HTTP template to greet a user. One of those prompts will generate vulnerable code in 100% of the time, the other one in the 0% of the time in the Llama family models. Can anybody guess which one it is? Even though you're not Python programmers. First one. Why? Because I personally cannot, and it's still an open question, but you're actually kind of correct. The first one will always render code that's secure, and the second one will always render code that's insecure. And basically, cross-site injection is that when you have a field that user can input things, and you don't sanitize, they can input a JavaScript that will completely take over your website. Can be pretty problematic for websites where you're entering your information, such as bank accounts. OK, so how do we try to understand how it works? Once again, coming back to general concept about neural networks, lower layers don't really care a lot of information. Higher layer tend to care more information and interconnect things better. So what we're going to be doing is we're going to be peering into the internals of code-generating LLM. Specifically, we're going to use the code that has been written by Anna-Maria Indres, who was in our lab about a year ago, that allows you to see how the LLM sees your prompt. It's a little bit hard to read because there's a lot of things to annotate. So what we say is that we ask this robust prompt, and we try to look at what the robustness word will be influencing. The robustness is highlighting. So we're going to see on the last layer all the attention maps, so basically which specific things this robustness word impacts. And basically what we notice is that robustness doesn't impact any code. Once again, sorry for formatting, you're looking at how LLMs thinks the word without the user interface in between. However, what it does impact is an LLM telling you why this code is secure, although it didn't impact the security of the code. If you focus on the safer keyword, the situation is exactly the same. It's not going to have any impact on the generated code, but it's going to have an impact on the explanation of why it's secure. So basically, prompting for robustness and safety is likely useless, at least in our context, except for the model claiming security. And that's something that if you talk with the security people, you will hear on over and over that if you try to ask model to be safer, it's going to say that it's being safer, but then it's still going to generate insecure code. OK, but it still works. Why does it work? So the next thing we looked at was, OK, we say that we are talking about Scala types. And I'm sorry, I don't think it's very visible, but here, oops, we're highlighting types and type system. And basically what we saw is that when you focus on the type, it actually does impact the HTML escaper. So the type and system are both important, and they're both actually what triggers the safe behavior. So the mention of Scala type system alone is what seems to trigger actual HTML escaping, likely because safe code tends to have comments related to type and time system, not vulnerabilities. Because people describing vulnerabilities are the ones analyzing code, but they're not writing it. People who write safe code use different concepts. They're not addressing a CSS cross-site injection vulnerability, that are doing proper sanitation, and they're usually doing it in Scala with type system. So the question, can we push Scala type system usage further in our model? Yes, that's what we call TypePilot. Basically, we take a first LLM. We ask it to generate the baseline Scala code for a risky task. We take a second LLM model that has nothing to do with the previous one. We ask it to find vulnerabilities in the code below, and then ask for the patch techniques. Finally, we take a third LLM, and we input both the baseline code, the critiques, and ask it to use Scala type system features to output well-typed Scala code. So we're not just asking to use type system. We are naming specific features. And this is what returns us well-typed Scala code. Now, some of you might have recognized this setting up as agentic because we have several LLMs interacting. We didn't add the compiler into it, so it's not as agentic as it could be. But the thing is, it works. It works wonders. Everything's correct. Q1 2.5 coder with type copilot clears everything in the tests that we did, including some real-world tasks such as matrix convolution that is hard for other model, including base model. Not only clears everything, the code that's generated is also safe, both for Q1 and code llama, if it compiles. Basically, if TypePilot compiles, it is correct and secure. And that's even before we go and talk to the compiler. OK, sounds great. It works in our benchmarks. How about real world? Well, once again, we are machine learning experts, not Scala. You, at Scala Days, however, Scala experts. So you can try it. The interface is up. You should be able to register. This demo is made possible thanks to Scale, with whom we have collaborated on multiple occasions. And if you use LLMs, you're going to basically have an interface with a Q1 base model and TypePilot that's going to be trying to use the agentic prompting pipeline with Scala type enforcement. And just so that you can compare yourself whether Scala types have any impact, the safe pilot, which is trying to do the same thing, but without mentioning types at all. And you can experiment with your own code, with your own edge cases. And I'm fairly certain that you're going to find edge cases where it doesn't work. So please tell us about it and how it went. Now, if you don't like the interface, but you'd like to deploy it yourself, Exascale has partnered with us to allow you to deploy the demo yourself and just run it if you're not a big fan of peering into Python code responsible for LLM deployment. No blame for you here. You can also contribute to TypePilot and look at the specific prompts and prop responses on which this presentation is based, or inspect your attention map with Viz Attention, where you want to run a model on your own prompts and try to see what's in the prompt is impacting code generation or not. However, while you're doing this, a couple of ideas about the future. Coding LLMs are here to stay. They're useful to both experienced and beginner developers, and the developers currently in training are likely to rely on them in the future. The languages are likely to live or die by how well they work with LLMs, which is unfortunate for extremely well lower resource languages that are going to be more niche and probably less used as the time advances. But the reality is, if you've interacted with developers in training, master students, you'll realize how much LLM code generation usage they have and how much it's likely to be continuing. The LLM code generation will not get safe. Basically, I alluded to really quickly, the reason why LLMs aren't really getting safe over the years is because they're relying on the bulk of training data. And some biases are present in the training data for all LLMs. So if the code has been insecure for first LLMs, it's probably because of the training data. Training data doesn't get thrown out, so it remains, so do the vulnerability. Critique and secure code generation seem to use separate languages that doesn't interact well. Something will need to connect them. Other safety mechanisms are required. And the third point is something that I have kind of hypothesized 2 years ago in Madrid, is that Scala is in a good place to persist and thrive in the LLM land. Lots of high-quality training data. Once again, the reason this works is because the type annotations seem to be correlated with secure code, which is a result of the work by you and other Scala developers who have consistently written good code if they've been typing it. Who've been consistently connecting good typing with good code. Scala also have bindings for type systems and formal verification, which are those additional safety mechanisms. Now, the question is, how can we make LLM Scala better? How can we make the formal verification actually work on the generated code instead of the LLM just ensuring that it should work without it really working? With that, I would like to thank you for your attention. This work has been sponsored by the CYD campus. Part of the research that I mentioned here is probably going to continue upon the open model release that has been announced by the Swiss AI initiative, of which we are part, where we'll be able to dive into what's actually impacted the model behavior. We'd like to thank Cyril Velez and Anna Maria Indres for their work while in our lab, and Oliver and Hamza for their very insightful advice on Scala safety and real-world usage. With that, I'll be happy to take any questions you have. Thank you. And just before I forget, for the 3 best questions, I have the examples of large language models in the cybersecurity to give out.
I have a question. First,
Sure.
Thank you for the really interesting talk. I was really super interested to see what you found out here. The TypePilot, that it works so well, you said that you don't just say use a type system, you say use specific features of a type system.
Yes.
So which features and how do you adapt the features to the program at hand, or is there a standard catalog?
So basically what happens is that we thought about adapting it, but we don't know enough about Scala features that can be used for it. So maybe there's a collaboration on figuring out what Scala type system features can be used to address different classes of vulnerability to have a more interesting prompts. But basically we ask refine types, traits, and seal traits as an example, or ADTs. And what we can see is that seal traits already have a lot of positive impact on the code being generated. This is an example of output. Oh, wait, haha, you're not seeing it. Up. Yes, much better. Yep. So basically, we just provided the static ADTs, refine types, traits, seal traits. And what we see is that they're getting used whenever we are, this is lower one. Whenever we are trying to prompt it for, Yeah, sealed trait HTML contact, so it has an impact. Similarly, if we look at the places where sealed traits has impact, we basically have the sealed trait HTML contact, which means that it's trying to wrap around it. It has an effect, but we didn't really go into depth of which types it should be trying to use.
That's, yeah, okay, thank you very much. I find this amazing that this could also open the door to, let's say, an empirical analysis of usefulness of certain program features for safety, not just by LLMs, but also by humans. So thank you.
That's definitely interesting. I think there's much more interesting perspective on how to teach LLMs that they can use this feature to address this vulnerability, especially for new features that are not yet present in the training data sets. So maybe there's something about creating a lot of example or GitHub repositories with permissive usage licenses so that they get aspirated and so the new mechanism gets included into the LLM. But once again, we still don't really understand how the training data impacts the model, but it's a direction we're moving into. I believe there was a question here.
Yes, thank you very much. That was really interesting. You mentioned that the code, if compiles,
Yes.
is safe.
Yes.
Have you tried also to actually have the compiler in the loop and reject if something doesn't compile and rerun it?
That's a great question. I believe Rory Graves and Carla has asked me the same question 2 days ago. The problem is that this is pretty fast when you're running the inference. The second you're starting to add the compiler in the loop, you offload things from the GPU to CPU, you run the compiler and you return it. It's fairly slow. We've heard rumors of people doing it in the reinforcement learning to make the model write the codes that compiles. We didn't try it, in part because of the overhead of engineering and how complicated to work the serving ecosystem for LLMs already is, even without adding reinforcement learning into mix. But that's definitely a great idea, and if you're interested in collaborating on this topic, let's talk during the break.
And if it's not much, you also mentioned we are children of the magenta line, so that means the skills go down when we depend too much on that. I've seen the same for doctors, medical doctors. They become less, well, they become worse when they use too much. So have you seen or studied that for programmers?
That's a paper that came out recently that basically says that doctors that use a lot assistant tools start losing their sharpness when the assistant tools are withdrawn. I'm not sure how generalizable it is because it's been only one report and there's other reports that say that doctors plus LLMs or just LLMs alone work really well. But in software engineering specifically, this is something that terrifies me because I've seen interest from people who have a lot of hiring decision on safety critical software, be really interested in using less skilled developers with LLMs, for reasons I think you can guess. And on the other hand, having worked with younger generation that have learned how to program with LLMs, I also think that there's a lot of skills that we'll need to retrain them on once we get them on board in our teams, because they tend to generate the entire program with all the features and then ask you if it's what you're expecting. And if not, you regenerate it and ask the same question. They don't really have the skill of like starting with a small thing that works, even if it's just a hello world, and then start adding features where they know that each feature is working. And then you later, if introduce a bug, you can do a bisect on GitHub, on Git, and figure out where it came from. Nobody in the room was aware of Children of Magenta Line, and hopefully you're all going to go and watch this video and then talk to other people so the idea gets out there. But this is really something that I'm concerned about going forwards and that I don't really see discussed at large. Does this answer your question? Okay.
Yeah, I think you had 3 different LLMs. Just curious how important that is versus could you just use the same one in a fresh context each time?
Yes. So what we see is that LLMs are actually really critical. Q1 2.5 coder works really well. CodeLlama 70B, not really, and DeepSeek Coder, despite the fact that it's based on QN 33B, actually doesn't work that well. We don't really understand why. Those models are open weight, but they're not open source, as in we don't know what the data they trained on, what was exactly their protocol that we are able to replicate. This is why I'm speaking so much about the Swiss AI Initiative LLM is because it's intended to be open source with all the training data available, with all the processes, with all the scripts, so that we can start understanding what impacts what.
Okay, actually my question was, you had a sequence. There's like a draft, first draft, then a critique, and then a fix me, and you said those are 3 different LLMs. That thing, yes.
It's the same type of LLM, but they're reinitialized from 0. So they don't have context persisting. One of the reasons for that is that based on how LLMs are trained, they're really good at looking at what's on the first half a page, pretty good at looking what's one over first 2 pages, and whenever you get over it, their performance decay, even despite the claims of really long contexts. That's why we focused on keeping it short and within the context window, because once you have something like this, it starts getting pretty long and pushing on the limits of where they're really good at performing.
Yeah, so on the slide where you're talking with the 3 different models, one of the models, the middle one, you talk about critiquing the code to look for particular vulnerabilities. Mm-hmm. Do you find that the quality of the vulnerabilities or the quality of the security of the code that comes out is better if you mention specifically different types of OWASP top 10 vulnerabilities?
Okay, so we can actually look at it together. Let me disable the CL traits. So basically, this is what the LLM sees, including the starting token, the system prompt, basically starting system prompt, user prompt, and basically everything that you usually will see as the user interface. However, there's way more happening in it, and those hidden characters have role. So let's see. Provided Scala function greets user has potential vulnerability related to cross-site scripting. So let's look at cross-site. So basically, this freezes the attention map. We're on the last layer for QN model. And basically, what we see is that cross-scripting impacts the first generated, but not really Scala type, and impacts plain text here, but not really much here. However, we can also focus on this cross-site scripting and see if this impacts something. And what we see is that this cross-site scripting impacts it having discussion about algebraic data types to represent HTML as a content model. So then when we look at disable the cross-site scripting and look at the algebraic data type, the algebraic data type starts impacting the case class. So basically, case class here, case class here. If you're familiar with the text, you can see that it's a new line that doesn't get rendered, because once again, we're looking at the bulk of output. So it looks like it doesn't impact directly. What it does, it impacts the generation of the header of the model that then impacts the code generation. And that's kind of the recurrent theme in LLMs. They need some scaffolding to generate. So whenever somebody talks about thinking LLMs, LLMs don't think. They generate scaffolding that they can later use to generate better code downstream. That's why the chain of thought prompting works, if you have ever heard about it. Does this answer your question?
Yeah, for the most part.
Good. I believe, Victor, you had a question?
Okay, I think it's the final one.
Thank you for a very intriguing talk and for great evaluation. I was wondering, my question is maybe a bit high level, but what can we do as people who author a Scala and maybe correct Scala to make this training, fine-tuning work better? So in terms, I mean, you mentioned the Swiss models, and what I'm hearing is that because of the goals of this project, is there was a lot of attention being paid in honoring the status of the code on which it is trained and so on, something that's not done everywhere. But then in the end, this might hurt actually performance on code and other things.
We don't really know yet. Once again, there's very few models that has been open weights and that has been coding. There has been, for instance, Bloom, a model that was released in 2022, that was open implementation of GPT-3, that was, I believe, using quite a lot of Scala in its code mix, around 7%. For comparison, QN that performs really well is only using 0.5% Scala code. However, it didn't clear any of our tests' functionality performance. So we still don't really know. We really need to only dive into this exploration of how code annotation, perhaps some reinforcement learning elements during the post-training impact the model behavior. And at this stage with the Swiss AI initiative, we're just releasing the first open source model. So that's an excellent question. I hope we'll be able to answer it in the future, but if you want to collaborate on it, it's a good moment.
Thank you.
Let's thank Andrei for his presentation, everyone.
Thank you.